then I can easily get this number, and it's not difficult to implement this algorithm actually. So we're gonna do the tricks that how to calculate this Ln and Rn for general n actually, no matter what n you have. Okay. So 100 is going to be really with 1000 it is going to be 0.333 2833, and this is 0.3338 and so on and so forth. So if you average down all these values, you're gonna see that the average of all of these values is really approximately 0.333. So you have really now a good idea that okay, this is really 0.333 area actually. Okay, 0.333 area. Now let's talk about, say, a little bit of general method to compute such areas actually. Okay, so if I, for example, now I say that let's take the same curve, okay, interval 0 to 1, and I have split it into really tiny parts of equal length actually. Okay, tiny parts of equal length. And first I'm going to take, say, left hand point, and then I'm going to take, say, right hand points actually. How many are these numbers? I don't know. So let's say these parts, let's keep them abstract, are, so it's like split this interval 0, 1 into, say, n parts. Okay, n parts. The question is, what should be the size of each of the interval? The answer is not really difficult. Why? Because what you can do is that, okay, see the length of the interval, which is 1 minus 0, and divide it by n. So you're going to get what? 1 over n. So 1 over n is the size of each subinterval. Okay? It's the size of each subinterval. And now, say for example, I mean, this n is a big actually. I mean, you can see that, okay, these are a lot of small rectangles, but you are seeing really a zoomed version of it actually. So therefore, you are looking at this. And now I want to do what? I want to, calculate the, say, area through, really right end points actually. So the right end points. It's going to involve some error, but right end point. Okay, right end point. This is going to do better. You're going to see that this is going to do a lot better actually. Okay? The more interval you increase, you're going to do a lot better. Okay? And so on and so forth. I want that you should swallow this, basic fact actually, because then the next is really, so the next is really, what do you call it? The rest is really based on this actually. Okay, so you have this. So I have split it into, say, this 0, 1 interval into n part, while this 1 over n is the size of each part. So this is really the size of each part. We mathematically call it a mesh actually. So what you are creating, so splitting the domain, splitting the interval into some number of parts of some equal length, you call it that you have created a mesh actually. Okay, so you have created a mesh. So what we should do now? Now let's say try to compute this in general. So what would be Rn? By the way, what will be the intervals now? The first interval is going to be 0 to 1 over n. The second is going to be 1 over n to 2 over n. The third is going to be 3 over n to 4 over n, yes, 3 over n to 4 over 2 over n to 2 over n to 3 over n, okay, and so on and so forth. The last one is going to be n minus 1 over n, and finally is going to be n over n actually, which is equal to 1. So these are the intervals that you have, in which you have split it actually. So what was the recipe? The recipe for creating the Rn was what? Really to, in each subinterval, take the right end point, compute the height of, the function at the right end point, and make the rectangle out of it. So the first is, what is the right end point here? 1 over n. So how can I compute the height at the right end point? So just substitute this value into the function, whatever function you have been given. So for the moment we have x squared, and multiply it, say, with the width of the interval, which is 1 over n. So f of n multiplied by 1 over n, then you're going to have f of, say right hand point, the other is going to be 2 over n multiplied by the length 2 over n minus 1 over n is going to be 1 over n, plus so on and so forth. The final is going to be f of, the final right hand point is going to be, so this is like n minus 1 upon n, and this is n upon n. So the final right hand point is going to be f of n upon n, which is 1, multiplied by 1 over n. So in this list, I took all right hand points and substituted into the formula. So what you're going to get? So you're going to get something interesting. So what is 1 over n? F of 1 over n. So f is x squared. So you're going to have 1 over n squared times 1 over n. One of the things that you can really see is that 1 over n is common in all. So you can, take this 1 over n out. So 1 over n squared, what would be this? So this is going to be 2 over n squared plus so on and so forth, and the last is going to be n over n squared actually. Okay? So n over n squared. This is what that you're going to get. Now I have to simplify this expression. Do you see anything common in all? So there is still something that is common in all, that is n squared, n squared, n squared, the denominator of each one of, these sums actually. So you can pull that out. So you're going to get 1 squared plus 2 squared plus up to n squared and 1 over n squared times 1 over n actually. So this is going to be 1 over n cubed. And now, what would be this sum? So this sum, if you remember, is equal to, this sum is equal to n times 2n plus 1, I'll make a list of it, n times 2n plus 1 times n plus 1 upon 6 actually, times 1 over n cubed. Okay, 1 over n cubed. So my final Rn that I get a formula for this is 6n cubed actually. So this is now a generic formula for Rn. This is now a generic formula for Rn, general formula. So in this, if you substitute say 4, so you're gonna get R4. In other words, the value of the 4 that you got here. So in this formula, if you substitute say 10, you're gonna get this value. If you substitute say 1000, you should get this value. If you substitute say 1000, you're gonna get this value actually. Okay. Now I can see that if these intervals are finite actually, so these are finite, there is still some error. Still some error. What if I increase, what if I split it even more? Even more. So you're going to say, in how many parts? Say, let's split this into more and more and more parts. So how to say it mathematically? So n is representing the number of parts in which you have splitted the interval 0 to 1. So if I increase this part, limit n goes to infinity. Okay, limit n goes to infinity. In other words, if you increase, so infinity is not a number. Okay, so you can say as your n gets more and more and more, what would be Rn? Now I know that how to calculate this limit. How can I calculate this limit? For example, when you have infinites and say such polynomials. So what you can do is that try to say take the highest power common from the denominator actually. So I can take, for example, n from this bracket. I can also take n. So if I pull out n out of this bracket, and so from this bracket I'll also take out say n. Okay, maybe let's say n. So if I pull n out of this bracket, so this is going to be 2 plus 1 over n. And if I pull say n out of this bracket, so it's going to be 1 plus 1 over n. Okay, 1 plus 1 over n, and divided by what do you call 6 and cube. So if you, for example, cancel out this 6 at cube and say substitute the limit, so what you're going to get? You're going to get 2 plus 0, and this is going to be 1 plus 0, and this is going to be 6. So if you simplify it, you're going to get what you call 1/3. So what does this interesting result is telling you? This interesting result is telling you that in this picture, if you will keep on increasing what do you call the number of intervals, and on each subinterval you make a rectangle, okay, then in other words, if you increase the number of rectangles, then the sum of the areas of rectangles that you calculated through right end point is going to be 1/3. Is going to be 1/3. And this is really, you can say, the exact area, what do you call, the exact area under this curve, y equal to x square, 0 to 1. So this is really the exact area of this 1/3. I can do a similar calculation for what do you call the left hand point actually, right hand point. Okay, so we did for the right hand point. Let's do this for the left hand point now. So let's calculate say Ln. So now I'm gonna compute the f at each of the what do you call right hand point, left hand point, and then multiply with the height actually. So I can do this. I'm leaving this for you. So do this calculation and you're gonna see that limit n goes to infinity, Ln is going to be also 1/3. Okay? You're going to be also 1/3 actually. So if you take say, if you split this picture, the domain of this interval into a lot of subintervals, and create a lot of rectangles, tiny rectangles through what do you call left end point, what would be the sum of areas of all those rectangles? 1/3. So from right end point you are getting 1/3, from left end point you are getting 1/3. So you're going to say that the area of this is 1/3 as well. And we saw it actually previously. Okay, so our estimate for the area by taking the averages was also 0.333 actually, which is a exponential, which is a decimal form of 1/3 actually, which is a decimal form of 1/3. Okay. So what is the generic recipe? So let's generalize this procedure. You can apply this procedure to any function that you like actually. and you can do the calculations. So let's generalize this procedure. Let's write a general recipe. Let's write a general recipe, and then you will have some exercises in which you have to apply this recipe in order to, what do you call, solve some integral, some not integrals, but find some area there. Okay? So imagine I have a function that goes like this, and say this function is defined on the interval. So in other words, the domain of this function is this line segment A to B. A to B. So what would be the first step? The first step would be to create the mesh actually. So, and by mesh I mean splitting into a lot of, what do you call, subintervals. Okay? Splitting the A into a lot of subintervals. Now, what is really, so say, I know about this number, that how many these subintervals are. So I have this interval A to B, and I want to split it into n parts. What do you call n parts? Say this function is some function y equal to f of x. Okay, y equal to f of x. So what should I do? What you can do is that split this into n equal parts. So I must say equal parts. You can split it even into the unequal parts, then, but the things would be then a little bit complicated actually. So we're gonna assume that, okay, equal parts. So if you are splitting this interval A into the n equal part, what is the size of each equal part actually? So the size of each equal part is going to be a number that is going to be a fixed number. I'm calling it delta x. What I'm calling it? Delta x. So what would be the size of the delta x? How to compute this delta x, which is the size of this each of these subinterval? Compute the length of the interval, which is b minus a, and divide it by the number of intervals, a number of parts in which you want to split this actually. So if you want to split it into 10 parts, divide by 10. If you want to split it into the n parts, divide by n actually. Okay, divide by n. And now let's give these, what do you call, subintervals, some abstract names actually. So let's call this first entry, say first segment, as x0. Let's call this x1. Let's call this x2, x3, so on and so forth. So this is xn minus 1, and the final is going to be xn. Okay? I know about the first part that this is A, and I know about the last that this is B actually. Okay, this is B. Now, if you splitted this A to B into n subintervals, which are those intervals? These intervals, x0 to x1, x2, x1 to x2, x2 to x3, and so on and so forth. The final is going to be xn minus 1 to xn. So I split it into these subintervals. Okay? By the way, if you can also write these x0, x1 in the terms of delta x and a and b. How? What is my x0? What is my x0? So my x0 is really a. Now what is my x1? So take this x0 and add this length of the interval. You're going to reach to what you call x1. Now what is the length of the interval? The length of the interval is delta x, which is fixed. You're going to say this is x1 is going to be x0 plus delta x. Okay? In other words, A plus delta x. What would be x2? x2 is going to be, okay, take your x0, x1 and add this, for example, length into it and reach to x2. And what is the length of this subinterval? Again, delta x. So the x2 is really, what do you call, x1 plus delta x. x1 plus delta x. But if in this x1 I substitute this, so this is going to be x0 plus, what do you call, delta x plus delta x. So my x2 will become A plus 2 times of delta x. So this is my x2. And you can guess actually what would be x3. So it's going to be A plus, so say for example from I want to reach from A to x3. So what is the distance? So A plus, this is 1 delta x, 2 delta x, 3 delta x. So x3 is really A plus 3 delta x. And similarly xn is really A plus, what do you call, n delta x actually. So these are also, what do you call, the descriptions of, generic descriptions of, what do you call, these endpoints. So how I'm gonna calculate, now this right sum, let me call it right sum, okay, or the sum through the right endpoint. So let's call it Rn. So how I'm going to calculate this Rn? The same recipe, that in each subinterval take the right endpoint and compute the height of it, compute the height of the function at the right endpoint. So if this is x1, this is really the height of it, and make a rectangle out of it. So take, say, f of x1, so this is the height of the rectangle. And what is the width of the rectangle? The width of the rectangle is fixed, is delta x. And then what would be the next rectangle? Take the right endpoint, f of x2 times delta x plus so on and so forth, f of xn times delta x actually. So this is going to be really the right sum actually. And then what you can do, for example, is also since this delta x is fixed actually, so you can say that, okay, sum up from f of x1 to f of xn and multiply it with delta x, and then calculate the limit of it and see what you get. So whatever you get is going to be, you know, the approximation to this area, a very good approximation to this area from the right actually, through the right sum. And what is going to be from the left sum? Ln. Then each subinterval take the left endpoint, in other words f of x0 multiplied by delta x, f of x1 multiplied by delta x plus so on and so forth. So in the last interval you have to take the left endpoint, so it's going to be f of xn minus 1 times what you call delta x. And then compute the limit as n goes to infinity. And this is really the recipe that, you know, the Newton thought of for finding the areas of the rectangle actually. So it's a fun recipe, okay? It's not that bad recipe actually. So here is the definition of the area of any function under, what do you call, the curve, area under this function f of x. So the area is going to be the area of the curve. So this area A is this shared value, limit n goes to infinity, okay, Rn, and limit n goes to infinity, Ln. calculate this, these two should be equal, and whatever their shared value is going to be the A actually. So we calculated this Rn and Ln for say f of x equal to x square, and we got the result actually. We got the area as 1/3. So this is really the area. So I hope you got that. You got the essence of it, that in order to find the area of the curve or under any curve, what you can do, that you can you can compute these limits. Say right end, sum through the sum of rectangles through the right end points and sum of rectangles through the left end points. Okay, or you can take the middle, doesn't matter. Okay, and calculate the limit of say Rn and Ln, and that would be the area actually. That would be the area. We're gonna do more examples. We're gonna do some more examples actually. Let's move to now let's move to, we have kind of, I mean, if you have grappled this idea very well, if you have understood this idea very well, we have kind of already covered the basic idea of what do you call the definite integrals. So I'm going to move to the what do you call the new notion of definite integral. Okay. So I'm going to write a definition. Okay. So again, say you have this curve y equal to f of x. Okay. And I want to really talk about this curve and the area under this curve. So let's start with that. Okay, this curve is defined on the interval a to b, and split it into a lot of subintervals. These are some. So assume that this is a zoomed version of a lot of intervals. Okay, and say give them names as x0, x2, and so on and so forth. Okay. So give them names. So let's call it x0, x1, x2. This last one is xn, and call this as xn minus 1. Okay. Xn minus 1. So we have this. And now let me give a definition of what you call the definite integral. Okay. Definite integral of the function between a to b. So what we did, we said that we have a function. So consider a function f of x defined on the interval a to b, okay, and then we divide a to b into say n parts, okay, and what are those parts? x0 to x1 up to xn minus 1 to xn, and then from each of these subinterval choose a sample point actually.